Good morning all. Today I'm going to build a circuit, but I'm going to start with the schematic of that circuit. So let's start drawing that. Well, it's a battery like so, and it's another battery like that. Now these are both 12-volt batteries, and then the rest of the circuit is simply a resistor here and a resistor here. Oh, it's a bit low down, isn't it? A bit high up, I mean. And that is my circuit. 2 batteries and 2 resistors. Now, one of the batteries is going to be a bit bigger than the other one, so let's draw that as a big outline like so. This one's a smaller battery. Didn't really think that through, did I? But never mind. And this big battery is being charged, so I'll just put an arrow going in with a solar panel and a solar charge controller. This battery is being discharged by a load, which is actually a little light with a PIR sensor. So the purpose of this circuit really is to transfer energy from the battery that's constantly being charged by solar to the other battery. And I thought I'd go through 2 resistors so that if ever there's a mismatch in the battery voltages, then the current will be limited by these resistors. Now I don't know what value these resistors are yet. I'm going to have to measure them. So let's have a look at the batteries in question. Well, the first one, the big one, is there in that wooden tub just outside my work zone. So it's this thing. It's a big car battery, 110 amp hour. It's being charged by my little PWM5 solar charge controller, and I'll show you the panel in just a moment. Now it could equally well be this big deep cycle marine battery, again 110 amp hours. Let's take a look at the solar panel that's keeping that big battery charged up. And well, it's this one. It's an 80-watt solar panel. It's actually in full sun at the moment. It's a very low winter sun. Now I can have additional panels charging that battery. I've got another 81 watt solar panel there, and there's a 100-watt panel up on the fence there. So I could put all these not directly in parallel, but I could put each one through a solar charge controller and then parallel them at the battery terminals. So I'd have 3 of these little charge controllers paralleled at the battery terminals, which is red and black, but with separate connections on yellow and black going to the 3 separate solar panels. Now the reason for doing that is because this has a current limit. I can't really take the current going through that controller above the amp rating of each of those panels, which is about 5 or 6 amps, because that's what this thing is rated at. Now the second battery, the smaller battery, is this one here. It's a little lead acid gel battery, 12 volts again, and it's on the opposite corner of the house. This is round the front, and it's powering this little LED light which lights up the front door area and that PIR sensor. And I should be able to trigger that PIR sensor just by covering it to simulate darkness. The light comes on. It only stays on for 10 or 20 seconds, but that has actually proved to be very good. It works very well. I desensitized that PIR sensor and it's just about bang on. But this has been running for about a month off that little, I think it might be a 12 or is it a 17 amp hour SLA lead acid battery, and I think it's getting a bit low. In fact, let's get a DMM and look at the voltage on there. So voltmeter on there, and oh yes, that's very low, 11.3. I've let that get a little bit low in charge. So what I need is to attach my 2 resistors between this battery and the battery that must be 20 meters away on the other side of the house, to transfer energy from that one, which is being charged by solar, to this one, which is being discharged by my little light. So my 2 resistors are here. Yes, it's this reel of light duty speaker cable, AWG25. It is quite light duty. 100 meters of this, I've got plenty of it. Got this cheap in the Homebase closing down sale. So let's peel off this cover, and take a look at the thickness or lack of this light duty speaker cable. So let's strip a bit of this back and just take a look at it. I've just noticed actually that it says 14 by 0.12 millimeters. So has it got 14 strands? Is that a circular number? Yes, I suppose it would be, wouldn't it? Because you've got one in the middle and then 6 surrounding that, and then presumably 7 surrounding those 6. No, it'd be 6 surrounding those 6. Why isn't it 13? Why is it 14? Why have they crammed an extra wire in there? That's weird. Anyway, it is pretty light duty stuff. There's the wire next to a 3mm LED for a size comparison. So yeah, let me find out how much wire I need. I think probably about 20 meters. And then somehow I want to try and measure the resistance of each of these 2 wires, and which are my 2 resistors. So I've made up a little temporary reel puller thing, so I can pull the wire from this position, which is fairly close proximity to my big battery, which is through there, pull that round to the front of the house so that I can see how much wire I need to link these 2 batteries together. Right, it's far too cold out here. My hands are just raw with cold to lay this cable properly, but I think that is going to be enough. So what I want to do now is measure the resistance of my resistors. So here's my piece of cable. It's probably around 20 meters. I'm just going to find both ends. I'll go for the black stripe side, and we'll attempt to measure the resistance of this. Now I know that this DMM is a bit rubbish at measuring low values of resistance, but I've put the 2 ends of the wire, actually not the black stripe, the other one, across the connections here. So let's see, turn the light on, see what it says. Oh, well, if that's true, and of course it's moving around, then that's a higher resistance than I anticipated, 9 ohms. But to get a more accurate measurement of the resistance of this cable, I'm actually going to connect it to my power supply. Yes, if I connect this piece of wire across the output of my power supply, then we know from Ohm's law, and that's R equals V over I. If I set this power supply to a 1 amp current limit, then the voltage across the resistor will rise up to a voltage which will be an indicator of resistance. I will be 1, so V equals R. Whatever voltage appears on here across that piece of cable, that's the resistance in ohms. So let's disconnect my piece of wire from these banana plugs which are in my DMM, connect them into the output of this power supply. Okay, that's wired up. Let's plug in 12 volts. Now let's set this thing to 12 volts because if this is 9 ohms, then we should get 9 volts across that wire. So 12 volts, and we'll set a current, how do I do that, of 1 amp, yeah. So we'll get 1 amp to flow, and we'll measure the voltage across that resistance. Now I want the 1 amp to be fairly exact, assuming this thing is accurate, of course. So 1 amp and 12-ish volts, doesn't really matter exactly what it is. Right, let's see how many volts appear across the output. There's our 1 amp, and the voltage is, oh, well, maybe my DMM's quite good. 9.09 volts. In fact, I think that did say 9.1, didn't it? So yeah, my wire is 9 ohms. So my total resistance between my 2 resistors, 18 ohms. And in some ways that's a good thing, because it means that even if these 2 batteries are different by, say, 9 volts of difference, this one is at, like, I don't know, 15, and this one is down at, what would it be, 6, then we're only going to get half an amp through our 18 ohms of resistance. So the current is never going to be enough to fry this wire. But there's always going to be a current flowing through this wire, these two resistances, if there's a difference in voltage between these two batteries. So whatever this battery is being charged up to, this battery will charge relatively slowly, probably through this 18 ohms of resistance, to the same voltage in order to bring the current down to 0, and therefore no charge is flowing between the two batteries. So yeah, 18 ohms should be good enough. Well, I suppose the black stripe should be negative, so let's strip that back, strip this one back, and let's get oh, that's interesting. That looks like the black stripe is a silver colored wire. That could be tinned copper, whereas the other one is uncoated copper. Maybe that's intentional. Yeah, maybe that's intentional so that you don't get your polarity mixed up when you're using this for what it's meant to be used as, speaker cable. So is this a speaker cable thing? People who are into hi-fi and stuff, to have one tin coated or whatever that coating is and the other one not, so that you can see the polarity. Is that a thing? Right, since we're connecting or soldering big terminals onto bits of wire, I've plugged my 12 volts into this quick charge compatible USB thing, and I'm going to use the TS80 soldering iron. So let's plug that in. The only reason I wouldn't normally choose to use this is because it's got this very big bit on the end, but that should be fine for putting crimp terminals onto wire. So let's switch that on. I can't remember what temperature I set this to. So my thoughts about this would be that this would warm up a bit slower because it's only getting 9 volts with a maximum of 2 amps. And yes, I suppose that is a bit slower than the TS100. Oh, I'm going to need some water on my sponge here. Let's do that while this warms up to whatever I've set it to. 320, is it? 330 or 40? Oh, far too much water. Flood. Right, let's put that in there. That's going to be a very wet sponge. Okay, so that's set to 320. Let's get some crimp terminals on. First things first, let's get some red and black heat shrink on here so that I don't have polarity issues when I'm out in the cold and my brain starts to fade and I can't think straight. Some nice black and red indicator heat shrink on there. Super. Now, someone suggested that these sort of fairly hard plastic insulating pieces shrink, and yes, they do a little bit, but of course the problem with this is that they're all red, so I don't want all red. I want red on one and black on the other, so I will take these off with my pliers, because I don't know what plastic this is, but it certainly doesn't have the same properties as... That's not coming off very well, is it? You want that little squeak. Yeah, it doesn't have the same properties as the polyolefin heat shrink with its proper 2:1 shrink ratio. So yeah, these are coming off. So how am I finding the TS80? Well, it's absolutely fine, and I'm not really noticing any difference. If I can get that thing to warm up. The main thing I'm noticing actually is the cable. Ouch! Oh, hole in the carpet. Yes, the cable, which is this silicone, is very, very lightweight and very flexible. I'd like to try and get, if I can, a similar cable but with 2.1mm plugs for the TS100, and then it would have the same sort of lightweight feel. Yeah, I just nicked the back of my finger with the iron. That made me jump. Right, let's put a bit of solder on the wire. It's probably too long actually. I'm probably have to cut that down a bit. Oh, this insulation's nice. It's not melting back. That's quite good. Yeah, I'll just cut that down a bit so it doesn't poke out the end when I put that through there. Still got my heat shrink, haven't I? Yep, that's on there. So let's warm that from the other end. Get it to warm through and poke that in. wait till it sets and grabs it. Now, can I put the heat shrink on there and will it shrink around the hot spade terminal? A little bit, but I'll have to finish it off with the heat gun, I think. Yes, I mean 18 watts is more than enough to heat up these crimp terminals to take solder in like that. That's ample. So I've done it again. I've touched the hot spade terminal. So yeah, the TS80 is nice. Got no issues with it at all. Let's heat that up from the inside again. Can't make a contact unless I've got a little bit of liquid solder on there. That's melting. In that goes. Hold it until it grips. Slide the red heat shrink on. Okay, a bit of hot air to finish these off. And they're done. That's for the small battery with the large connectors, and we're going to put the smaller connectors on the other end because that's going to go on my little terminal blocks that are on the bigger battery, the power supply in my work zone. Okay, let's do that. Tin these two wire ends. Like so. Probably have to cut those. That's a bit blobby. Probably have to cut that down a bit and feed it through there. Now on the TS100 you press both buttons to turn it off, but this is more of a sort of rocker switch, so I'm not sure whether I can't press both buttons. It won't let me. So how do I turn this off? Press and hold that one. That takes me into settings. I don't actually know how to turn this iron off. Perhaps I'll read the manual. Yeah, it doesn't actually say. It just says, while TS80 is heated, do not touch the soldering tip to avoid being burnt. Yeah, thanks for that. Don't take out the tip while the thing's on. Doesn't actually tell you how to turn it off. Perhaps I'll just pull the plug. So I was just thinking, I'm going to connect these two to the little gel battery out the front. And then I'm going to run this sort of down the side of the house and connect it up to my big battery, which is being charged with solar. And I thought, well, I don't want to connect those together when this is on the gel battery. But actually thinking about it, that battery is only, well, it's only 11 volts at the moment, but say it's 12 and this is 18 ohms, there's only going to be 3/4 of an amp flowing through this. So even if I connect this to the gel battery and short these out, 3/4 of an amp. It's not going to do any harm to this cable, is it? Right, should we test this? Because what I'm going to do is connect these small terminals to the battery out there in the work zone, probably through the fuse. That's a 15 amp fuse. And then I'm going to short the other end with my ammeter and see how much current there is. Bit of fun. So my wires are connected directly across the big battery out there. Here it is in here, and here are the ends. Shall I short them together? Let's see what happens. 18 ohms, remember. And of course nothing happens because very little current is flowing. Let's measure it. Right, I've put this on to the 10 amp setting. Probably 13 volts out there on the battery. 18 ohms. Let's put that across there. And yeah, we got 0.7 of an amp. And no drama shorting this end. So I don't have to worry about these shorting while I thread it alongside the house. Let's take this pair of wires round to the front, attach it to the other lead acid battery and charge it up. Right, front garden lead acid gel battery. I've attached the positive and I can still short my wire coming from the big battery round the back onto there. That doesn't do any harm, but will putting it on the negative lift that voltage? Let's have a look. Yes, and up it's going. Now it's going to be a modest charge rate. Have I got that connected onto there properly? Let me attach that properly with my screwdriver and spanner, and we can watch that voltage go up. And there it is, fixed on there. And yes, the voltage is creeping up. Now, that's going to be a fairly slow charge because there is only about 2 volts difference between the battery here and the battery at the back, and we've got 18 ohms, so we've got 1/9 of an amp. Let's call it 100 milliamps. So that's a very gentle charge of this battery. So that voltage is going to creep up ever so slowly, but eventually this should get up to 13.5 volts, which is the voltage that the solar charge controller around the other side will lift the other battery up to. It'll just take a fair amount of time. And I've just been thinking, I wonder if this PIR light, which comes on only for a few seconds each day, could actually run not off a lead acid battery. There's far more charge in here than is actually needed, as long as it's being fed from the other battery. Maybe I could replace that with a supercapacitor, but I'm not going to do that today because I'm freezing cold. So that's it. Cheerio.